In Chapter 4, Combinational Logic, Chapter 5, Sequential Logic, and Chapter 6, Counters and Registers, and Chapter 7, FSMs, we have seen these um, different types of logical structures that we can analyze and design. And what we have mainly considered or concentrated was functionality, how these circuits operate, how we can analyze or how we can design this type of circuits. Now, in this chapter, we are going to talk about or see the design considerations. So apart from the functionality or the logical operation, we are going to talk about the integration, the timing, and some asynchronous interactions that we need to consider in order to build a proper digital system. So before we get into the details, let's talk about some of the overview about integration of the circuits. Now, integrated chip or ICs or integrated circuits, whatever you want to call over there, we have different types of packages because we have to mount these on a printed circuit board. So when we want to mount these, they have got a different legs and the types of packaging that we have to solder it and so on. And the integration is actually what we have put inside of that package. Now, the integration is actually from the early days to now or different types of projects, it can change. What do we mean by that? The number of transistors that we can fit in a chip or for an application specific chip or a processor or something like that, they have got the scales. And for example, we can say small scale integration is around less than 10 gates. Or medium scale integration, we have got 10 to 100 gates. Or large scale integration, we can have 100 to 1,000 gates. And very large scale integration is, which we are currently using in most of the microprocessors and the microcontrollers, 1,000 to 100 millions and billions of transistors or gates that we can fit. So that's why we call this VLSI, which is a very large scale integrated circuits. Okay. So this is what we call it integration. So the number of gates that we can fit on a chip, it's actually the integration. And in chapter 1, we have talked about the transistors because we are using CMOS technology, complementary metal oxide semiconductors. So we have got two types of transistors, PMOS and MOS, that we need to use in order to build logic gates. So one is complementing the other one. That's why that they are called complementary metal oxide semiconductors. So gate, source, drain, gate, drain, source, and so on. And they're working in an opposite way. So another important metric that we consider when we are doing a design is fan-in. Now, what is fan-in? When you are having a gate, you will normally see one or two inputs or maybe three input gates. So you might have a gate with 1, 2, 3, 4, 5 inputs. That's also possible. That's not wrong. But the problem over here is when you have a large number of inputs, that means you're increasing the number of transistors in one gate over there, and also you're increasing the capacitance in that gate. And this is actually going to slow down your operation of the gate. Okay, so we have to charge those capacitors, we have to discharge them. So it's going to take some time. It's actually it's going to limit the performance of the device. So rather than having a 5 input gate, what we can do is we can have 3 input one, and then we can also implement a 2 input one. Okay, and then we can have 4 inputs, or maybe you can have one more input. So you can use 2, 3 input gates, and you can do it like that. So that's also acceptable. Okay, so we can use it this one as well. and we can at least minimize that fan-in problem. Okay, you have multi-stage gate over there rather than having a one gate, but this will have a performance limitation compared to the multi-stage gate. So it's like a trade-off. So which one to use and what will be the best. So you have to do those calculations in order to have a proper gate design. Now, another metric is the fan out. So the fan out is, okay, we have got a gate again, and there are some other gates or maybe some other lines that, and this gate has to drive, this gate output has to drive all other gates. Now, when you think about it, this is actually forming a load capacitance at the input of each of these gates, right? Now, the problem over here is, as this signal is coming from this output over here, now if you are trying to fit, think about it this way, you are one person and you are going to reach to different places at the same time. Maybe you can do it one at a time, that's not a problem, but you serve that one, you serve that one, somewhere here you start to get tired. Okay, you don't have that much of energy to serve that person or this job. So your energy is going to degrade and degrade and degrade. So what is happening is uh, when you have a large fan outs like these that you need to serve a number of gates over there, your signal is going to degrade. Okay, so okay, you are going to get maybe a 3 volts, but it's going to be a degraded 3 volts. It's not exactly 3 volts. So it might cause a problem in a way that your circuits might, your capacitors might not be charged fully in order to get the valid logic level. So fan out is a problem if you are driving large number of inputs together. So it might hurt the gate performance and it might cause a problem. Now, so what we can do is for the fan out, we can actually use buffers or inverters. So we can restore the logic value into proper value before it gets into the gate. So what we can do is, once again, we have got the gate driving. We can fit with the inverters or the buffers for each of the lines. Okay, we are increasing the number of gates over there, but actually we are keeping the values over there as well. Okay, this can be a buffer as well. It doesn't need to be an inverter, depending on the logic operation that you are doing. You can feed a buffer, so you are actually buffering the signal over there. So buffering signal means restoring to its original voltage level or logic level. So this can help us to not to degrade the performance or hurt the performance of the gate. That's what fan out is. And this is also demonstrated over here. And noise margin. Now, noise margin is also important because when you think about it, let's say we have got a input coming in. Okay, that fits into one of the inverters. Now, if there is a noise, okay, what will happen is, if we try to generate an output, as this is going to be an inverter, 0 is going to be 1. Now, you can have a signals like this. A little bit delayed. Oops. And so you might have something like this, distorted. So what is happening over here, over here, over here, or maybe here, or maybe here. Now, if you do remember in chapter 1, we have mentioned threshold voltage of a transistor. So when it's reached to certain points like 0.7 volts, your transistor is going to be on or maybe off. Now, as you're expecting one over here, and because of the noise that's degraded to somewhere here, that might turn off the transistor. So if you are feeding this signal to somewhere else, to another logic, it's going to be appearing like a logic 0, not logic 1. Okay? Or this one. So as you have a spike over there, this might not be a logic 0, as it's around 0.7, for example. It might turn on the transistor on the next level. So noise can be a problem. So we have to minimize the noise in the circuit. So there are a couple of things, like you can get the noise from the power lines, like the VDD and the ground. You might get a noise from another chip next to it, or maybe some very noisy truck or something like that. So we have to be careful when we are designing this, that we can minimize the noise in the circuitry. Okay, so that's another design metric. Then propagation delay. So what is propagation delay? Now in chapter 4, we have seen multi-level logic design. So we have got AB going in to another gate. So C is over there. Then it's F. Now the propagation delay, it's where we send the input A, and when it is going to appear as a logic value. So the longest distance that the gate signal or input signal is traveling through the gate is actually telling us the propagation delay. Now, easiest way of demonstrating this delay is using a simple inverter. Now, when we look at over here, the input signal, generally we are checking the 50% when it is on the rising edge, okay? So input is on the rising edge, or it might be in the falling edge, but in this example, we are just taking the high to low transitions. So when it reaches to half of the transition, from that point, and whenever we start to see the output is changing, because this is going high, inverter, it has to go low. Now, this is high to low transition, because that one is going high, that one is going low. And then when it reaches to high, and then it's going to change again, then we have got low to high transition, okay? So the maximum propagation delay is taking the maximum of those two parameters for the worst case conditions, okay? So these are all defined based on the output transitions. We will do an example and you will understand how these are affecting it. So this is actually the maximum, or you can have the average propagation delay as well. Again, high to low transition and low to high transition. When you first send the input, how long will it take to see the output? And that's what's happening here. So you send in the input signal until how long will it pass to see the reaction on the output? That's what propagation delay is. Okay, so let's do the first example related to these design metrics. An integrated circuit logic family has NAND gates with a fan out of 8 standard loads. So NAND gate can drive 8 loads. That's what it's saying. Okay, and the buffers with a fan out of 16 standard loads. So buffer can drive 16 loads. Okay. Sketch a schematic showing how the output signal of a single NAND gate can be applied to 38 other inputs. Okay, so single NAND gate we have got, and we need to apply to 38 in total. So how are we going to do that? Because one NAND gate can just drive 8 loads. So we have to divide it into some buffers, okay? So 38 gate inputs that we are going to derive in total. Now, if I use 2 buffers, that will drive 32 loads, right? So this is going to be a buffer 1, oops, which can drive 16. Then I have another buffer which can drive another 16. Now this is in total 32. Now what left is 6. So in order to drive another 6, I can drive them directly from this load. Okay, so in the end, I can say that this is 6. So 6, one goes over here, one goes over here. So the NAND gate is driving 8 loads, 2 buffers, and 6 normal outputs. And each buffer is driving another 16 loads, 32, and it's going to be 38 in total. Okay, so this is how we can divide them equally so that NAND gate cannot drive more than 8 or buffer will not drive more than 16 loads. So we can actually have a same voltage level at each input. Okay, another example that we can consider is the propagation delay example. So with this one, assume that the average propagation delay is given with TPL-HL and TPL-H, high to low, low to high transition. Find the delay from each input to the output in the below figure by finding the TPHL and TPLH for each path, assuming TPHL is 0.20 nanosecond and TPLH is 0.36 nanosecond for each gate. And from these values, find average delay TPD for each path. Okay, so we have got different paths over here, C and D to F, B prime to F, A to F, and B, C prime to F. Now, C and D has got the longest path because it has to go 1, 2, 3, 4 gates. B prime has to go 1, 2, 3 gates. A has to go 1, 2 gates, and B, C prime has to go to 1, 2 gates. So they might give us different delays. Only A and B, C prime are going to give us the same delays because they are going into 2 stages. But these ones are going to be different. So there are 2 ways of solving this question. One of them is, which I believe is simpler than the other one. Now, when we consider inputs C and D, TPD, C and D. Now, what do we have over here? We have got 1, 2, 3, 4 gates. Okay, so 4 gates actually going to provide us 4 times 0.20, which is going to be high to low transition. Okay, high to low, or let's say over here, high to low. Right, so that's going to give us 0.80. This is high to low transition in 4 stages. Then I can find out CD's low to high transitions, which is again 4 stages, and that has to be 0.36. So 4 times 0.36, it's going to give us 1.44. Now, in order to take the average, we just need to add both together. So TPD, CD, it's going to be 0.8 plus 144 is 2.24 divided by 2, 1.12 nanoseconds. So that is the propagation delay that we will observe from CD to F. So it will take 1.12 nanoseconds that we can see the reaction of the inputs through the output. Okay, so that's CD inputs. B prime, we have got 3 stages. So TPD B prime, it's going to be, so high to low, 3 times 0.20, which is going to be 0.60, and TPD B prime low to high, is 3 times 0.36, which is going to be 108. So then TPD B prime, it's going to be 1.68 divided by 2, 0.84 nanosecond. Okay, so from this point to output F, we need 0.84 nanosecond. So we can repeat the same thing for A. So A has got 2 stages, B, C prime has got 2 stages, so we can all calculate those together. So TPD A and B, C prime, high to low, so 2 times 0.20, which is 0.4, and then we have got TPD maybe C prime low to high. That's going to be 2 times 0.36. Okay, so in the end, this is going to be 0.72. So then that's going to be 1.12. And then divided by 2, this is going to give us 0.56 nanoseconds. So for each stage, as you can see, we can find out the average propagation delay. Now, this is one way of solving this. On the slides, there's an alternative method. So what it does is, okay, so each stage will have 2 low to high and 2 high to low, okay? So in order to find high to lows, and then 2 high to low and 2 low to high. So it's actually separating them inside of that as well for each of these gates. This is also possible, but in the end, you are going to get the same answer. So I believe the way that I've done over here, it's simpler. You can do it in either way. It's up to you. So the same applies over here. Then we have got 3 stages. So 2 times high to low, 1 times low to high, and then 2 times low to high, and 1 times high to low. So it's going to give you the same result again. And the same applies for the last stage as well. So this is how we can use these propagation delay, and we can find them through the given circuit timings.